Let me get started. Thank you so much, Ennis and Robert, for having me today. So what I'm going to talk about is insect scale micro aerial robot powered by soft artificial muscles. If you look at the keywords, right, there are two keywords in my title, being micro and soft. I want to spend the first 5 minutes or so explaining to you what are micro robot in this context, and then I want to spend the rest of my time explaining to you a new class of micro robot that are driven by soft artificial muscles. So first, when we think about robots, I think most people nowadays would think about large-scale robots, such as legged robots, humanoid robots, or trains or airplanes that span the scale of meters to the scale of hundreds of meters. On the other end of the spectrum, you can think about using MEMS technology to make very tiny robots on the scale of microns to tens of microns. What I want to focus on today is talking about insect scale robot, and specifically they range from 1 to 5 centimeter, and they weigh from 10 milligram to 10 grams. So as a quick example, when I was a grad student about 10 years ago, I worked on a project called the RoboBee. And back then, the idea was to create a robot that has similar size and functions as honeybees in nature. So very quickly, let's address several questions together. The first question is, why do we study microrobotics? And to me, there are two answers. The first one is by leveraging interesting physics at the centimeter scale, we can enable new functions. In this case, by leveraging flow similarity, we can teach the robot to use the same set of wings and actuators to both fly and swim. And more than that, I can turn this around. I can use microscale robot as a platform to investigate interesting physics at the centimeter scale. By looking at the flow field that's generated by a flapping wing robot, I can infer about the lift and drag generation mechanism of a flying insect. Second question, what makes microrobot unique? And the short answer is that at this scale, inertia become less important and surface effect become a lot more important, so new property arises. For example, you can drop a microrobot from fairly high above and it sees small amount of changes to its performance. And more than that, my colleague has shown that you can teach a microrobot to jump off the surface of water, something that's very challenging, if not impossible, for larger scale robots. Okay, so last question, what are potential applications of microrobot? Well, in the short term, I can think about a lot of them. How about put a tiny camera on board of this legged robot and put this legged robot inside of a turbine engine? So what I'm showing you is a cross section of a turbine engine, and then teach this robot to climb inside of this turbine engine to look for cracks. In the longer term, our vision is to use a swarm of ubiquitous and multifunctional microrobot that can operate in realistic environment. Okay, so this picture is still fairly far-fetched. What we are trying to say is we want to use a large number of microrobot in the search and rescue mission. And of course, there's a lot of challenge that we need to solve. So toward the end of this talk, I want to revisit this picture and identify some of the key challenges and gaps we still have to achieve this longer-term vision. So at MIT, our research has two themes. I want to spend rather short amount of time to go through the first theme and then focus on the second theme today. But first, let me say that our first research theme is that insect scale robot can do multiple things in complex environment through leveraging unique physics at the centimeter scale. And I want to show you two case studies, one on a hybrid aeroaquatic microrobot, and the other one on a hybrid terrestrial aquatic microrobot. So if you want to build something that's on the scale of insect and that can fly, you probably want to look into nature for inspiration. It turns out that we can approximate the flapping wing motion of an insect with 2 degrees of freedom motion. And in most of the flapping wing robot design, what happens today is that the wing stroke motion will be actively controlled by a actuator, whereas the wing pitch rotation is passively mediated by a compliant flexure and the aerodynamic forces. So in our lab, we have set up a experimental system that allows us to capture hundreds or thousands of those flapping wing videos. so that we can then extract the flapping wing kinematics. And in fact, not only can we extract the flapping wing kinematics, we can also analyze the underlying fluid flow. So this is a video showing what we call at scale particle image velocimetry experiment. Essentially what we do is we put oil particles in a fully enclosed chamber, illuminate the particles with a laser sheet, and then compute the cross correlation of the measured velocity field. And then you can see on the right, now you can see the growth and shedding of leading edge vertices, which will give you intuition on the lift and drag generation. And in addition to having experimental tools, we also have computational tools that allow us to compute the pressure profile and isovorticity profile on the wing surface. So now we have the suite of experimental and computational tools. Why are they useful from a robotics perspective? So here, what we want to do is we start with asking a question in physics, and specifically we want to ask the question about, is there a similarity between flapping wing locomotion in air versus flapping wing locomotion in water? And if there is similarity, what additional functions can we achieve? In this case, we came up with a project in the sense that we want the same robot to be able to fly, to swim, but also making transitions from air to water and from water back into air. Without going to all the technical details, let me show you the robot design. Compared to the old robot, this new robot has new wings for added lift force. It has 4 buoyant outriggers for maintaining stability on the water surface. And most interestingly, it has a gas collection chamber for performing water to air transition. And let me show you how everything works. So first, we can start the robot at the bottom of the tank, and the robot will flap its wings at a low frequency, in this case about 10 hertz or so you can swim up to the air-water interface. Once it reaches the air-water interface, we are going to turn off the wings and then turn on a parallel plate. And what it does is that the parallel plate will start to split water into a combination of hydrogen and oxygen. And the increase in buoyancy force will push the robot wings out of the water surface. And not only are we using hydrogen and oxygen to increase buoyancy force, we are going to use them as combustion fuels. So I recommend you to pay attention to the next part of the video, okay, because it's going to be quick. In the next video, we are going to ignite the mixture of hydrogen and oxygen, and you can see we triggered a microscale combustion that allowed the robot to leave the water surface. This combustion finishes within 1/1000th of a second. So this is one of the fastest combustion process that's, although very short, is powerful enough to break the water surface and shoots the robot back into air. Okay, so in summary, we have created a 175 milligram robot that is capable of flying, capable of swimming, can transition from air to water, more impressively, impossibly transition from water back into air, and also passively land on ground. Following this same thread of thought, I want to very quickly go through a second robot, which is a robot that can work on land and also on the surface of water. Okay, so in the past example, we spent a lot of time to talk about how a tiny combustion to break the water surface tension that is otherwise very difficult for the robot to break by just flapping the wings. And on the other end of the spectrum, as humans, we barely feel surface tension at all. And the reason is that at our scale, the surface tension force is less than 0.1% of the inertial forces we can generate. If we can build a robot somewhere in between, specifically if the robot weighs about a gram or so, and if it has a contact lens on the order of 10 centimeter or so, then all of a sudden, the surface tension forces and the inertial forces are on the same order. Now we can introduce new functions. So again, we start with a question in physics, that is, how do we control the magnitude of surface tension forces? And if we can control surface tension forces, what additional functions in robotics can we enable? In this case, we created a new project in which we want the same robot to be able to work on land, on the surface of water, controllably transition into water when it wants to, and eventually transition back on land. And without, again, going to the technical details, let me say that we used a phenomenon called electrowetting. And the idea was that we're going to send a high voltage to the water surface through a electrowetting footpad so that we can modulate the surface tension contact angle, which allow the robot to controllably sink into water. So let me show you how everything works in a video. In this case, we start the robot on the water surface. It will now transition and walk down, we start the robot on land, you transition onto the water surface, so now it's swimming on top of the water surface. I recommend you to now focus on the side view. This robot will now sink by turning on its electrowetting footpad. So now the robot is fully submerged underwater. Once the robot is under the water, it will then climb this incline slowly to return back on land. So again, what we demonstrated is in a robot that weighs about a gram can do multiple things, such as walking on the water surface, on land, and underwater. And sometimes those type of locomotion is challenging, if not impossible, for larger scale systems. And recently, we want to push for more functionalities in this robot, specifically by teaching this robot to climb on ceilings and walls. And we again use capillary effect. So what we did is we put an adhesion pad on the belly of this robot, and we leverage two phenomena. We use a normal adhesion force, that is because the curvature of the contact angle changes, that allow the robot to adhere to the surface. And also we use a lubrication effect in which we allow the robot to slide along the surface without needing to engage and disengage from the surface. So this turns out to be a very simple but effective method. Now I'm showing you a video of inverted climbing, right? So the camera is looking top down, and the robot is using this capillary adhesion force so that it can climb on an inverted surface while it's completely passive stable. Turns out this is much faster than climbing with electrostatic adhesion. Okay, so again, let me conclude my first research theme, which is that microrobot, although being very tiny, they can do very complex functions in complex environment. Now let me take a step back and zoom out a bit and say that our longer term vision is to create a swarm of ubiquitous and multifunctional microrobot that can operate in a realistic environment. And let's now take the opportunity to think about what are the performance gaps. So far, I've shown you two examples of microrobot that can operate at high frequency and are very precise. In my field, my colleagues are solving key problems in microrobotics by putting sensors, controllers, and power sources on board. But I want to point out that microrobots are still limited compared to insects. Specifically, insects can effectively interact with the environment, and also they can operate in a large number. Whereas it's extremely difficult to make a lot of microrobot effectively, and all of the demonstration I'll show you involve a single microrobot. To solve this challenge, I propose that we look into soft robotics, because soft robots are robust and they can safely interact with the environment, and we can make a lot of them cheaply. And over the past 10 years, there's a lot of techniques for putting sensors, controllers, and power sources on soft robotic systems. What I want to point out is that soft robots also have their own limitations. Specifically, most soft actuators are slow and they're not as precise as rigid actuators. As a consequence, most of the commercial robots that we see are driven by rigid actuators. Our goal in MIT is really to address key challenges in both fields by looking into a new direction in which we call hybrid soft rigid microrobot. And the theme that I want to push for is that what I envision future soft robots should be is that not only should soft robots be safe and compliant, they should also be agile and controllable. And I want to show you a few case studies that we have been working on in MIT over the past few years. Okay, so what I want to show you today is a flying robot driven by a dielectric elastomer actuator. The unique part of this robot is that it is driven by a muscle-like soft actuator, but it still have rigid appendages such as wings, transmissions, and wing hinges so that we can precisely control its motion. And because I'm combining soft and rigid component, hopefully I'll be able to show you some emergent properties such as resilience to collisions and injury. So what I want to do today is to answer three questions with you together. The first question is, can a soft robot fly? Prior to our time, it's extremely difficult to fly any robot without a electromagnetic motor. And second question is, well, if I can fly them, why soft? What are unique capabilities of soft robots? And finally, the third question is, what's our longer term goal with this class of robots? So first, let me try to convince you that indeed soft robot can fly. Okay, so as a grad student, I played with rigid actuators for about 7 years. Piezoelectric actuators are great because they are high bandwidth and precise. That's exactly what you need for flight control. But they're also kind of difficult to deal with because they have tiny strain. And as a consequence of having tiny strain, if the wing collide into an obstacle, it's very easy to crack a piezoelectric actuator. In MIT, we developed a new class of dielectric elastomer actuators on the same scale. And the unique part of those soft actuators is that they still can operate hundreds of times per second while having large strain. And just because it's intrinsically soft, it's tolerant to assembly error, so we can make a lot of those soft robots effectively. And if you look at how this soft robot is made, it has rigid components such as airframe, transmissions, and wings, which allow us to have very fine control of the flapping wing kinematics, but it also has a soft actuator in the center for driving the robot systems. So about 5 years ago, we assembled this robot, and this was one of the first flapping wing flight that we are able to film. This robot in this high-speed video flapped the wings at 280 times per second. And from this high-speed video, you can really see the elongation and contraction of this soft artificial muscle. And more than that, also about 5 years ago, we demonstrated the first lift-off flight performed by a soft driven robot, right? Again, you can see the elongation and contraction of this artificial muscle really behaving like true muscles. And I used to make this joke, which is that for a soft roboticist, this is a very exciting moment because for the first time, soft robot is able to lift off and fly. But if you are working in aerorobotics, this is useless in the sense that it flips over within 0.1 seconds, it's intrinsically unstable. So the question is, how do we catch up in terms of the flight capabilities of soft systems? So over the past few years, our lab spent a lot of time trying to understand the nonlinear properties of soft actuators at high frequencies and then wrap controllers around those soft actuators. About 3 years ago, our lab demonstrated one of the best hovering flight performed by a sub-gram aero robot. So this 0.6 gram robot was demonstrating a 20-second hovering flight, and it was so stable, it feels like this robot has been affixed to a particular position in space. And again, back then, about 3 years ago, that was the longest flight and also the highest performing flight performed by a sub-gram robot. If you look at the flight quality, the maximum position error is on the order of 2 centimeters or so, and the maximum attitude error is about 2 degrees or so. So since then, we are trying to push for longer and longer flight time. About a year ago, we have been able to double the flight time to about 40 seconds. And then as of a few weeks ago, we reported a recent study in which we are able to fly the robot for 1,000 seconds in a single flight. And I'll come back to this new robot platform toward the second half of my talk. Another thing we want to demonstrate is we want to show heading control during flight. And what I show you so far is while the robot can stably hover around the set point, it could not keep its heading angle. Imagine in the future if I want to put a tiny camera on board and teach this robot to sort of fix its gaze at the flower, it would be very difficult. To solve this problem, what my student Nemo did is he inclined the robot unit during the assembly process, so we can use a component of the lift force to generate yaw control torque. And as a consequence, we can get quite good heading control in this system. So when the robot is flying, now you can see the robot first turns left, and then it will turn right, and it will turn back to face front, and then it will land. So in some sense, we can now get 6 degrees of freedom control in a subgram aerial flying robot. Hopefully at this point I've convinced you that indeed soft robot can fly as good as rigid robot at the subgram level. But the more interesting question I want to answer is why soft? What are interesting about those soft systems? So now what we want to show is that we want to show unique properties of soft flying robot. So in this case, for example, we want to demonstrate the soft actuators are robust. I can repeatedly run a wing into obstacle and the soft actuator will survive. And more so, how about flying the soft robot near a cactus? How about cutting part of the wing off or put a lot of needles into the soft actuators? Or how about trying to demonstrate aggressive maneuver, namely turning the actuators on and off at very fast rate so you can perform a somersault? And also, because we make everything in-house, how about showing electroluminescence that is showing to show the robot can shine out light during flight? So first, let me show you collision recovery. When the robot is flying, we can gently push down the robot, and the robot will be able to recover to the hovering set point. Now, I want to say the first video is not very impressive yet. Most quadcopters can do this as well. What starts to get interesting is that if I start to hit the actuators during flight, or if I start to hit the robot wings during flight, right, the robot will maintain its stability. Imagine hitting the propellers of a quadcopter when it's flying. It's probably not going to turn out very well. And in fact, what's going to happen if I hit the robot so hard that it cannot recover? In this case, the robot simply bounces on the floor and then recover on to the hovering set point, simply as a consequence of being small and having low inertia. Again, very challenging for larger scale systems. And in fact, I want to push this a little further just to look at failure mode. It turns out that wing hinge failure is a common mode of failure. When the robot is flapping its wings, sometimes the torsional stress will cause a crack in the wing hinge, which propagates through the wing hinge within a few cycles. So when the robot is flying, you will see a wing will fly off, and the robot will lose stability and will plunge downward very quickly. This is in sharp contrast of what insects can do. The insect wings can be fairly worn out, yet the bees can still fly very well. And there is a community of colleagues who are interested in studying the neurological control of flying beetles. And what they do is to probe the neurological control signals, they will put electrode into the flight muscles, yet the beetles is still able to fly. So we want to demonstrate a similar level of resilience to damage. Namely, we want to ask the question if the robot, for example, can fly near a cactus. So we have identified 3 types of things we can do to the robot. We can either put a lot of needles into the soft actuators, we can cut a significant part of the wingtip off, or we can try to burn a big hole in the actuator. It turns out that we can use a phenomenon called self-clearing. Because this soft actuator is made of a very thin and compliant electrode, whenever there is some damage or defect, we can pump in a high voltage to self-isolate the defect so the bulk material or the actuator can still operate. So in this example, we have a robot in which one actuator has been pierced 10 times, a wing is being cut off, and another big hole is burned in the other actuator, yet the robot can maintain a similar flight performance. So this is a level of resilience that I would argue that has not been achieved even in rigid driven systems. Another thing I want to show is aggressive maneuvers. I like to use somersault as an example simply because somersault really favors smaller systems. When you shrink down in size, the time scale of your robot becomes faster, and as a consequence, the speed in which you can do this somersault also increases. At least in simulation, we show that our robot can perform a somersault within 0.15 seconds, which is faster than any of the existing aerial robot out there. So let me show you something we have been able to do about 4 years ago. Okay, so this is a somersault showing in real time. This is probably a little bit too fast to see in real time, so I'll play the same video at a slowdown rate. In this case, the robot takes off and hover around the set point, and then it will accelerate upwards. Once the robot reaches a targeted set point, it will make a somersault. Okay, in this case, it cannot really recover altitude, so it has to bounce on the floor and then recover to the hovering set point. And I'll show you a more recent somersault later on in this talk. But essentially in this demonstration, what I really want to demonstrate is that it combines agility and also robustness. Another function that we have been able to demonstrate is electroluminescence. Turns out that fireflies are quite amazing animals, that when they fly, they shine out light and they use that as a way of communication. And because we make our soft actuators in-house, we can embed electroluminescent particles in the transparent elastomers so that when the actuator operates, the alternating electric field will excite the electroluminescent particles. And as a consequence, when the robot flaps their wings, each actuator will shine out a different colored or different pattern light when they operate. And as a consequence, we can generate pretty fun videos. This was one of the first projects that I worked on when I moved to MIT. Back then, I have 2 students, and we all pull out our iPhones so that we can take fun pictures or videos with our iPhones. Well, you may ask that it looks nice, but why teaching the robot to shine out light? It turns out that for the robot to fly, you need to use a very expensive motion capture system that tracks the position of those infrared radiation markers. But now, if each actuator can shine out a different color or pattern light, you can think about those as active markers. So instead of using infrared radiation to track the motion, we can now use vision-based tracking. And it turns out that just with a few iPhones, we can get fairly good tracking qualities. So that was our first effort in trying to fly the robot in outdoor environment. And recently, we're also trying to make a lot of those robots cheaply. So my graduate student Nemo has been experimenting with 3D printing. At least we can now print the not so precise parts, such as airframes with a commercially available 3D printers. And as a consequence, for the first time, we are able to fly 2 robots together. So in this case, we are able to fly 2 robots collectively while they carry a long and flexible payload. This would otherwise be very difficult to carry by a single robot. In fact, we have so much fun that when we are flying, we put our lab name on it. So we are the Soft and Micro Robotics Lab in MIT, and you're definitely welcome to visit us when you're in Boston. So to summarize, our second chunk of our work, the theme of our research is demonstrating that soft robots can combine robustness and agility. By robust, we mean soft robot can survive collisions and injuries, and by agile, we mean they can perform somersault and can reach a maximum flight speed that's now more than 1 meter per second. And that's considering the robot length scale is on the order of a few centimeters. And also by unique, we mean that they can shine out light or they can fly in a swarm, which would be difficult for similar sub-gram robot at this scale. In the last 10 or 15 minutes, I want to tell you about our recent push for new functionalities in this system. So the second chunk of work, I'll be presenting this for a couple of years now, and I've been also hearing feedback from people. Based on the feedback, we really wanted to work on a new platform that can get us addition or improved flight capabilities, as well as a platform that allow us to work toward flight autonomy. But if I look at the older platform, usually the feedback I got is the robot works great, but it looks ugly. And the reason that it looks ugly is because it has sort of 4 identical units, has 8 pair of wings, And also because of a pair of everything, it's not only taking more time to make, but it's all easier to fail. If any of the wing fails, then the robot loses stability. And also I reserve so much area for placing the wings, I really can't find an area for placing power electronics and sensors. So until recently, we have been working on a new platform that looks a little bit smaller. So from wingtip to wingtip is about 4 centimeters. But more so, what I want to show you is that this newer platform is a lot more capable in terms of flight. What I want to show you today is this new platform can demonstrate much improved flight capabilities, and also it supports our recent effort in investigating various aspects of autonomy. So first, as you can see, this robot has now much, much longer wing hinges for reduced stress. And what that does is it's dramatically improved the robot endurance. Previously, microscale robot fly for seconds or tenths of seconds. Now, in recent work, we are able to fly for 1,000 seconds in a single flight. So this video has been played 100 times fast forward, right? This is orders of magnitude improvement compared to prior work. So why is it important to fly for 1,000 seconds? Well, because the robot endurance is so good now that we have time to tune our flight controller. So now we can, for example, show the robot can track trajectories, right? So some of you can probably see that the robot is tracking 3 letters, and this is a relatively small, slow flight, meaning that the robot's average flight speed is on the order of 10 centimeters per second or so. But because it's flying slow, it's very accurate. It's able to land exactly at the same platform in which it takes off from. If I generate a composite image of that flight, it looks like this. Okay, so it can follow or trace those letters very precisely. And now if I increase the flight speed, it will not be quasi-static anymore. It will be dynamic. In this case, the robot is trying to follow a infinity sign, and what it does is that now you can see some pitching during flight, and the robot can now trace this trajectory at about 30 centimeters per second, considering again the robot is only about 3 to 4 centimeters in the longest dimension. And now I want to show you a longer flight. I don't know if you can hear the audio, but if you can hear on your end, this robot really, when it flies, hums like a bee because the robot flies at about flap the wings at about 330 hertz. So when it flies, it really sounds like a honeybee. And in this video, the robot is tracing an infinity sign that's rotating. So if I stop the video and show you the trajectory, it will look something like this, right? It will trace this infinity sign while it rotates. So in this 30-second flight, the robot traces about a 10-meter long trajectory. Again, orders of magnitude than what subgram robot was able to do. And then we can also talk about agile maneuvers such as somersault. So this is now the most recent somersault we're able to do. You can see it's much, much more controllable than before. So in a slowdown video, again, the robot takes off, hover around the set point, and then now I'm showing the somersault by slowing the video down by 40 times. The robot makes 2 consecutive somersaults, and immediately after completing the somersault, it will be able to catch its attitude stability, and then it will return to the hovering set point, and then it will land at the takeoff position. A lot more agile and controllable than before. So in summary, this newer platform is a lot more long endurance. Compared to other subgram robots, it's really orders of magnitude better in terms of lifetime. And when it's following trajectories, it's now flying at twice the speed as before, while the position error is on the order of 1 centimeter or so. And if we measure agility with the metric of rotation speed, then our robot is not only faster than any of the existing aerial robot, but also than a lot of the insects that we can find in literature. Now, I'm not claiming that we are faster than any of the insects there, but I think there's just no motivation for insects to do multiple somersaults and compete in this way. Okay, so all of the demonstration I've shown you so far rely on a PID controller. People who know me knows that I think in my field, the challenge really resides in the hardware limitation, so that I'm happy with always pushing with newer hardwares, but using a PID controller. Since we have this newer platform, I think I'm convinced that now there's a lot of opportunity with control. So in collaboration with Professor Johnson Hao in MIT, we are now working on much more sophisticated control architectures. For example, colleague has been implementing model predictive control and then compressing them with a deep neural net so that we can achieve much more aggressive flight than what we can do with the PID controller that I've just shown you. This is a 10 times slowdown video. And the reason that I'm very excited about this flight is that if I look at the composite image, now the robot is pitching at 45-degree pitching angle and is able to accelerate from this point to this point within, is able to accelerate from 0 speed to 1.2 meter per second within 15 centimeter. Let me remind you that in the past slide, we said that the PID controller can achieve a speed of about 40 centimeter or so. So this is, again, a 300% improvement compared to the PID controller. And until very recently, my student has been able to show quite good flight maneuvers. If we see it in real time, now this flight looks like this, right? It can sort of zip by very, very quickly. So if now I show you a slowdown video, then you can see the robot pitching angle during flight is really quite aggressive. And when I show this to colleagues, I think the feedback I heard is that now the robot really fly like insects. And not only can it do point to point, it can also follow quite fun trajectories. So this is one of the sort of optimized trajectory by this model predictive controller. And you can see that if it's sort of flying at 0.7 meter per second or so, it can follow the trajectory quite well. And then the maximum speed we can get is much larger than 1 meter per second now. Another thing is with this newer platform, we can demonstrate hybrid locomotion. I'd like to use hopping as an example. Hopping is very difficult, and I think the most successful hopping robot I've seen so far is the Salto robot from Berkeley. And it is very impressive, mainly because that when the robot hops, it has to do a lot of planning and control when it's making contact with ground. And that is very challenging because it means within a short period of time, you need to use very complex mechanism to execute a lot of control. Instead, in collaboration with a former colleague, Papang, we have a different idea. Instead of making very complicated mechanisms, how about if we make a robot, a hopping robot that's 100 times smaller. And the key idea here is that instead of making active control during the stance phase, we're going to use the wings to perform low power control in the jumping phase and letting the stance phase be completely passive. And turns out that if we go into the modeling, this is really advantageous because the contact is now passive, we don't care about the surface property as much as also the inclination angle. So the hopping process become a lot more robust. For example, we can show the robot can hop on a lot of different surfaces, such as it can hop on soil, can hop on ice, okay? And when it hop, you can also hop on glass. When it's hopping, you can also pour water on it. And all of those are done by the same PD controllers. And also it can hop on grass and hop on wood. And when the robot is hopping, you can also rotate the hopping plane, and the same controller will be able to take care of that as well. Another fun thing we are trying to demonstrate, this was with the older system, is we want to show that because now you are small, and by small, I don't mean the size being small, I mean the inertia being small, you can now leverage impulsive interaction between robots to demonstrate new functions. Previously, aerial robots tried to avoid each other. Now we can show a 0.7-gram robot can hop on top of a 20-gram robot, so it can hop over a large gap, right? Otherwise, it would be very difficult for larger scale quadcopters to perform. So hopefully I've convinced you that with this newer platform, we can really demonstrate a lot of fun functions with sub-gram robot. The last 5 minutes or so, I want to show you our longer term goal toward flight autonomy. If you visit our lab, you will see that to fly a sub-gram robot, we need a lot of hardware. Specifically, we need a lot of motion capture cameras, we need a lot of outboard compute, and we also need a lot of high voltage amplifiers. The goal of our research in the next 5 years is to shrink all of those offboard things to something that's onboard. Okay, so recently, in collaboration with our colleague Farrell Helbling, we are putting sensors on board. Specifically, we have an IMU, a optical flow camera, and a rangefinder. And by wrapping very simple observers in our controller, we can demonstrate fairly high quality control with onboard sensing. In this first video, we are flying with onboard IMU, so onboard attitude control, but the position control is still relying on a offboard Vicon motion capture system. As you can see, the onboard IMU sensing is really quite high quality. In the next video, I'm going to show you complete sensing autonomous flight. Right? In the picture in the video on the right, what I'm trying to show is that the Vicon camera is completely switched off, and the robot is able to completely rely on the suite of 3 onboard sensors to hover around a set point. It's not perfect yet compared to motion capture camera, but I think we are making very good progress at that point. So in my view, I may be biased, I think sensing autonomy and compute autonomy is within reach within a few years. What's most difficult is, of course, power autonomy. In the past 35 minutes or so, I spent a lot of time to tell you about the good properties of self-actuators. But what's really challenging is they're much less efficient compared to rigid actuators. If I compare the first version of self-actuators to piezoelectric actuators, you can see that they have much lower power density, the robot has much lower lift-to-weight ratio, and it requires much higher voltage and less efficiency. With this spec, it's almost impossible for the robot to fly with onboard electronics. But because we can make everything in-house, we know exactly what to improve. As of a few years ago, we have came up with new elastomers for making the actuator, so we can significantly pump up the robot performance. And as of 2 years ago, we have come up with this new fabrication process that allow us to now operate at much lower voltage. I know for a lot of you, 600 volt still sounds very high, but because now we are at 600 volt range, now we can look at tiny component that can allow us to build onboard electronics. So first, let me say that whatever we have been able to achieve with 2 kilovolt, we have now been able to achieve at the 600 volt range. And that, from a power electronics perspective, is extremely helpful because now we can make very preliminary tiny circuit that can boost a low voltage in DC to a high voltage in AC for driving our actuator. So about 2 years ago, we came up with our first version of onboard electronics that weighs about 130 milligram that can be carried by a unit of our robot. That's 158 milligram. Okay, and what it does is that this component, this circuit element, can boost a 7.7 volt input voltage in DC to a 600 volt and 400 hertz voltage in AC, so that we can drive so we can get quite good flapping wing videos. Okay, and also about 2 years ago, for the first time, oops, I don't know why the video stops, but if you trust me, we demonstrated a very short liftoff flight while the robot takes off with this onboard electronics. Now we are still very far away from achieving power autonomy because we don't have a good battery yet. So the state of the art right now of what we can achieve is the robot can take off its own circuit, but we don't have a tiny battery. And that is really something we are trying to push for in the next few years, which is coming up with tiny batteries and incorporating that with our power electronics. With that, I want to say that there is also a newer version that we are working on, and the goal is to continue to drive down on the actuation voltage. So hopefully we can continue to improve the transduction efficiency of the entire pipeline. Also, the last slide is I want to say that we are also very much interested in pollination. This is a very meaningful application, and it turns out that pollination is a lot more complicated than just teaching the robot to land and take off from flowers. There's a lot of things you need to do to be able to shake off the pollen from a flower. And that again is still preliminary. So hopefully I have something more to say in the coming years. Finally, I want to zoom out a little bit and say that our longer term vision, again, is to use a large number of micro robots and apply them in realistic environment. What I want to say is we have made fairly good progress in terms of the hardware. I think the robot now is capable and reliable and agile, but we really not want to push on in the next 5 years or so is to thinking about the power electronics and control logic for those systems. With that, I want to thank my past advisors, Professor Rob Wood, David Clark, and Jane Wang, my collaborators. But most importantly, we are a relatively small group in MIT, but a lot of work that I present today are really led by my student. With that, I want to stop here and take questions. Thank you.
Yes, thank you so much, Professor Chen. This was a really nice presentation. Are there any questions here or in Zoom?
There's one.
Oh, okay. There is a question in Zoom.
Yes, so I pull up the question. So the question asked me about the limiting factor of the flight time, right? I think there are two parts when we talk about flight time. One is in the longer term, people will ask about the amount of energy that we can store in the battery and etc. So if we think about the amount of energy the battery can store, I think we are looking at the upper limit of about 300 seconds. But in practice, they're really limited by the amount of power that the battery can deliver. So I would say that if we are ever going to achieve a power autonomous flight, at least in the first trial, we are probably looking at about 10 seconds of power autonomous flight. And the other part about a limiting factor of flight is on the mechanical issues of this bee, right? The bee, when it flies, flap the wings 330 times per second. So there's a lot of stress both on the flexures and also on the actuators. In the older version, in which I was saying that the flight time is about 10 seconds or 20 seconds, that's because the wing flexures tend to fail very quickly. It turns out that in the old design, in the first few iterations that I've shown you, the wing flexures, has a lifetime on the order of 100 seconds or so. And because you have 8 flexures and any of them fail, means the robot will fail. So on average, once you pass about 20 seconds, some flexure at a certain point will fail. In the recent work, we redesigned all of the flexures in such a way that we have the idea of reducing the torsional stress in the flexures. So right now, really, we haven't seen flexure failure for a long time. So now the limiting factor of flight time really comes back to the actuator. What happened is that the actuator typically have a lifetime on the order somewhere between 500,000 cycles of actuation to 2 million cycles of actuation. So that essentially converts to about somewhere between 30 minutes to 2 hours of operation. So, a good actuator probably can last for about 2 hours, and a bad actuator probably will need to be replaced every 30 minutes. So that's why right now we're flying for about 16 minutes or so in a single flight, and the cumulative repair time for this type of system is on the order of 2,000 seconds or so, which is about half an hour. Does that answer the question? Okay, so let me just move to the second question. It says, in a swarm setting, how do the units coordinate with each other? That's a great question. So to be honest, we haven't really thought too much about multi-agent control algorithm. I think there's a lot of expert in MIT. So in the demo that I show you, right, essentially you can think about the two robots are still controlled by the motion capture system, which are then controlled by a central planner. So in some sense, we have a controller that knows exactly where each robots are and then control the coordination in that manner. If we talk about sort of trying to fly a large number of them, then yes, I think then localized control is important. Or in the future, I think, for example, attitude stability should be done on board, but sort of this higher level, swarm level control still need a central planner for some sort of coordination. But I think in short is, I think the hardware is capable of flying a swarm, but in terms of software, there's really a lot of things that we need to explore on. Okay, so I'll move to the next question. The next question is it possible to use any other type of signal for the actuator instead of electrical signals? So that's a great question. I think my honest feeling right now is, for the past 10 years, I've been working with flying systems, and all of the flight-worthy micro-scale robot rely on electrical control. And that is because the time scale of those are extremely quick. And when I'm running the controller, my controller are running at thousands or tens of thousands of hertz when they're doing control. And that's where electrical control systems are really good at. You can have very precise high frequency control. I think we are collaborating with Professor Cameron Alban, and we are thinking about a combustion-driven flying robot. Of course, that solves the problem of energy density, but of course, when you're using combustion, then high-frequency control becomes an issue. So again, I think it's a promising direction that we still need to explore. But from the perspective of control, I would say electrically driven system is the most convenient to work on. And if you use any other type of other system like pneumatically driven or combustion driven, the control will become a lot more challenging. Okay, so I'll move to the next question. What were the key challenges between the versions that allow the reduction of 2 kilovolt to 600 volt? Yes, so you can think about dielectric elastomer actuators as a soft capacitor, right? So I think in Rob's lab, you're also working on electrically driven soft artificial muscles. When you're making any sort of electrostatic driven actuators, essentially it's a capacitor. So the challenge is really how to make thin elastomeric layers or liquid layers. The smaller the separation, the lower the voltage you can get to. So the 2 kilovolt version, I think the elastomer layer has a thickness on the order of 35 micron or so, and the 600 volt version has an elastomeric thickness on the order of 10 microns or so. And once you go to thinner and thinner layers, one, it takes a lot more time to make because then you just need to stack up more layers, but two, you make sure the quality of those layers are good, right? What I used to explain to people a lot of times is not only do you need to make a layer that's 10 microns thick, but it also has to be, tens of centimeter in area so you can roll them up into a device. So you're making something that is large in one dimension, small in the other dimension. That's why it's particularly challenging. So if any of you are interested in making sort of coming up with new techniques for making thin elastomeric layers, I'd love to talk more about this. Okay, so the next question is there any heat-related issues linked to the actuators used, and how do you handle them? That's a great question. In fact, in my first paper that we published in Nature, we used a thermal camera to look at the temperature signature. Those robots, those actuators, when they operate at flight condition, they tend to heat up quite quickly. And specifically, the actuator tend to heat up from room temperature 25 degrees Celsius to about 70 degrees Celsius in 80 seconds. That's what we have been able to characterize about 5 years ago. Now, let me mention that it heats up very significantly because of the resistive loss in the electrode. So if you want to reduce the heat problem, there are two ways. One is, of course, use less or use more conductive electrode, but two is just simply operate your actuator at lower frequency. If you operate at 500 hertz, it will heat up very, very quickly. But if you operate at 50 hertz or 100 hertz, then the temperature increase will be a lot slower. And the other thing I want to say is the actuator, at least heuristically, seems to be okay with handling high temperatures. Again, we are able to operate it at 330 hertz for 1,000 seconds, and the robot and the actuator still can still operate. So yes, I think heat will be generated, but I don't think it's as severe as causing the actuator to fail or anything in the time scale of tens of minutes. Okay, so let me move to the next question. Regarding to your future development, what role do you think bioinspiration could play for insect scale or insect-like navigation techniques? I think that's a great question. And honestly, we have been just thinking about sensing autonomy, right? So what I can say is that I really want to collaborate with biologists to think about how insects address some of the challenges. what we learned, for example, is if I use a gyroscope to stabilize the robot, that's not very power hungry. That probably takes about a few milliwatts of power, considering the robot is consuming hundreds of milliwatts per flight. But it turns out that achieving position feedback is extremely costly. If you think about anything like optical flow, if you think about anything like time of flight sensor, you have to shoot down some infrared radiation and wait for the radiation to bounce back. That actually takes tens of milliwatts, right? And there's a lot of compute that's needed for optical flow. So my current hypothesis is that I actually don't see a lot of insects will be able to hover stably at a particular position in space because it's very energy hungry. So I think what we need to do is to collaborate with biologists and identify behavior patterns. For example, low power optical flow, etc., that the insect use, so that we not only emulate the navigation techniques, but think about what kind of navigation method can allow us to save the amount of energy that we can use for trying to perform those type of maneuvers, right? What's the least amount of energy we can use, for example, to teach the robot to land on a flower? Okay, so next question. Are the robot weatherproof? That's a great question. As of this moment, no. One of the big weaknesses of this robot is it's really sensitive to moisture. So actually, there are a couple of days in the summer that we cannot fly. If the humidity in the room is higher than 80%, I think the robot tend to die very quickly. So in some sense, yes, you can possibly address this problem by coating the actuator with parylene, with a very thin layer of parylene. But no, at this current moment, if you operate this robot in high humidity environment, it will not perform well. Okay, next question, is flow control through micro robots wings a consideration you are exploring to increase or optimize flight, or is it already a well-optimized stage? So I've actually, as a grad student, spent 2 years studying, again, the flapping wing aerodynamics. We've done a lot of work on CFDs and at-scale particle image velocimetry. This is not a fluid mechanics talk, so I don't want to spend too much time. But let me say that a lot of the trade-offs that we are struggling with is because we have an under-actuated system. We just have one actuator, and we rely on passive fluid structure interaction. My hypothesis is that if we can have 2 degrees of freedom, we can definitely increase the net lift. I'm not so sure about efficiency, but in terms of increasing lift, if I can also control the wing pitch dynamics, then I think we can further increase the payload of this system. Okay, and the last question, is there any tutorial or guide to build such kind of robot for experiment? We don't have a tutorial yet, and I have to be honest that this robot is pretty difficult to make, and even within our lab, not every student can make this. I think, to be honest, this is a problem that our entire field needs to address. So the best, I think if you really want to build this robot, of course you can read our papers, but I think the best thing to do is either come to my lab, shadow a student, or come to my advisor Robert Wu's lab and shadow a student for a couple of months. And let me be honest, I think the test for our student is, if I have an incoming student by the end of their first year, if they can build independently a robot and fly them, that's already a success. So there's a lot of small things we need to teach you in terms of fabrication. So yes, if you're interested, please talk to us. I think the best thing to do if you want to build those robots is to come to a lab and then shadow the students, and then slowly you can learn all the fabrication techniques. Okay. Is it possible
Okay.
that robot learn complex motions from insect videos through reinforcement learning? Yes, I didn't talk about this work, but we recently have a work published in RoboSoft, and my student will be there and presenting that work through reinforcement learning. We are not learning from insect videos, but rather we are learning from our models. So yes, I personally see a lot of potential in reinforcement learning. It's just, to be honest, we haven't had a lot of exploration in that area yet.